Hi, thank you. That was very nice introduction. Uh, one thing about that roadside geology of Washington book that I just got to add is that my co-author was Daryl Cowan, who was my um, uh, thesis advisor for both my master's and PhD at the University of Washington. So it was it made for an especially great collaboration, if you will, just to, we're now like really good friends because not only was I his student back in the late 1980s and early 1990s, but then we just continued this collaboration and we're both really happy with the book. So I just had to put out a little plug there for Daryl because he wrote all the introductions and he's got such a great perspective on Northwestern geology. It was really great to do that with them. So anyway, I've got a slideshow here where I'll be talking just kind of an overview, if you will, of Pacific Northwest geology, and I guess if you have questions, they'll just appear in the chat. Is that right?
Yeah, that would be a great way to do it.
Okay,
Just
and
type your
then we
question in
can
the
kind of
chat.
run through them at the end, so you can type them in as you think about them. So anyway, I'm thrilled to be here, even though I'm not here at all. I'm actually in Florida visiting my mother, so it's kind of nice to sort of feel like I'm back in the Pacific Northwest. Anyway, so we'll get on with these slides. Um, and let's see. Here we go. Okay, so I guess everybody here has noticed that there's really awesome landscapes in the Pacific Northwest. This is at Bandon Beach in Oregon. There's also, of course, the Cascade volcanoes. This is a photo I shot a long time ago looking over Mount St. Helens towards Mount Rainier. In Oregon, we've got the Cascade volcanoes continue south all the way actually to Lassen Peak in Northern California. But these are the Three Sisters volcanoes on the right. And here is Mount Bachelor, and then there's an extinct volcano there, Broken Top. If you go up to northern Washington State, you get in the North Cascades, which are not volcanic. They're mostly metamorphic and intrusive igneous rocks that have been uplifted from some depths to the Earth's surface, and now, as you can see, they're being heavily glaciated. If you go to the east of the Cascade axis, you get into much drier climates. This is looking into Yakima Valley, and down in Oregon, there are all these pluvial lakes, which are now, many of them are covered in salts. This is Lake Abert, and there's basin and range country down there as well. So there's a lot of diverse physiography. It's just amazing landscape. And you can look at the physiographic map like this, which is from the USGS, and you can see that it can fall very nicely into a bunch of different physiographic regions, which were really convenient for writing these roadside books because each chapter then would be a different province. And so we'd have an introduction to the chapter, and then that would be followed by the road guides within that province. And that's the physiography. But of course, there's a real connection to the geology. So here's just a schematic cross section across Washington State, beginning with the subducting Juan de Fuca plate here and the Olympics. And it's pretty complex, but the main thing I want you to see is this heavy red dashed line here, which separates the basement rock from the cover sequence. And so for this talk, what I plan to do is first off start in the basement. I'll talk a little bit about Siletzia, which if you're in Washington State, call it the Crescent Formation or the Crescent Terrain, but it's all part of this great big terrain, generally called Siletzia. Then I'll move over and talk briefly a little bit about the edge of North America, which you can see in very northeastern Washington State. And then after that, kind of lead a sort of little field trip, if you will, up the Columbia Gorge, which is shared by both Washington and Oregon. And that would encompass just rocks within the cover sequence, located generally about where this little rectangle is on the schematic cross-section. But before I get on to that, I just want to make sure everybody is up to, feeling comfortable with plate tectonics. And I just want to take just a second to address that, because plate tectonics plays such an important role in how the landscape of the Pacific Northwest forms. So the idea behind then plate tectonics, and my apologies if this is too basic for you, but is that the Earth's outer shell is called the lithosphere, is broken into these gigantic fragments called plates. And as those plates move around, that's what causes earthquakes to take place. That's what causes a lot of volcanic activity. And that's what causes mountain belts to form. And here in the Pacific Northwest, we have these three plates: the Pacific Plate, the Juan de Fuca Plate, and the North American Plate, all quite close together. And so the next slide will be a close-up of that. And so here we've got now the Pacific Plate in gray, and Juan de Fuca Plate in the light blue. And then beginning at the red line here, the Cascadia Subduction Zone, is the North American Plate. And you can see over here, here's Oregon and Washington State, and the stars are the Cascade volcanoes. And so in what you're seeing then is the Juan de Fuca Plate. It's pulling away from the Pacific Plate, and it's diving down or subducting underneath the North American Plate. So in a three-dimensional view, it would look something like this, where here's the Juan de Fuca Plate pulling away from the Pacific Plate and going down underneath the North American Plate. And as it does that, then it heats up and it causes it to dehydrate. And that water then rises into the bottom of the overriding plate here, the North American Plate. And that causes melting to take place in the North American Plate. And then that melting, that molten rock then fuels the Cascade volcanoes, which is why they form a line that's parallel to the subduction zone. So I just can't overstate how important this is. If you just look at the geology of the Pacific Northwest, it's really dominated by the fact that we're right at an active plate margin for millions, hundreds of millions of years. So we see that today. We see the Cascade volcanoes forming this line that's parallel to the subduction zone. But when you step back into the past, you can look at the rocks, and you can see that same thing holds true. So for example, if you think about these volcanoes, they are fed by magma from below, but not all that magma reaches the surface to erupt. Much of it stays underneath the surface, and it cools down and it crystallizes into an intrusive igneous rock, probably the best known of which is granite. And we see a lot of granite that's related to this subduction zone setting throughout. We see it in the younger granites in the Cascade Range. We see older granites up in the North Cascades. We see them in the Okanagan. We see them in the Klamath Mountains. We see them in the Blue Mountains of Oregon. So we know that, and some of these things are like 140 million years old. So this kind of setting has been dominant in the Pacific Northwest for a long, long time. We also can see how the subduction zone setting has greatly influenced that. Well, it's basically responsible for the growth of the continent. And if you look at this diagram here in the lower right, you can see the oceanic lithosphere diving beneath North America. And you can imagine there being some like big oceanic plateau or series of islands or something that are oceanic islands that are sticking up off the seafloor. And as they come into the subduction zone here, let me find my cursor, they come into this subduction zone, they're gonna like jam up that subduction zone and basically cause it to stop. But the two plates are still converging on each other. So eventually it's gonna break, and it would break farther outboard away from the continent and to continue that subduction. And as it does that, then this body here that originally jammed up the subduction zone, it then basically gets added on or accreted onto the continent. So if you take another look at that cross section, you can see then all these basement rocks, they have all been accreted onto the edge of the continent, one after the other. First, this one Q for Quinellia, then all the terrains in the North Cascades, and then finally, most recently, Siletzia was accreted. And this is Washington, and if you look at Oregon, it's very similar. You've got some of the terrains are different, but still you've got a bunch of accreted terrains added one after the other to the edge of the continent. And they are then all overlain by this cover sequence of sedimentary and volcanic rocks that have formed since accretion of an individual terrain. So to start with Siletzia, the hallmark of Siletzia, or the crescent formation, really are these pillow basalts, these big kind of blobs. The scale here, this is probably about 20 feet from top to bottom. And these things form because of undersea eruptions. You can imagine a volcanic vent expelling blobs of magma into this pretty high pressure, deep sea environment, and the basaltic blobs, then they chill on the outside and they settle down to the bottom of the seafloor, but they're still a little bit malleable on the inside because they haven't chilled on the inside yet. And so then they settle one after another and conforming to each other's shapes. And that's what we see with these pillows. And we see that throughout much of wherever Siletzia is exposed. So if you were to look at a geologic map of the coastlines of Oregon and Washington, and the coast ranges actually, wherever there's purple are exposures of Siletzia. And it goes all the way up to the northern tip of the Olympic Peninsula, in fact, even on to southern Vancouver Island. And here's a photo then from taken near Mary's Peak in Oregon that shows a cross-section of some of these pillows. And you can see this very characteristic fracture pattern that's perpendicular to their surfaces. So that's Siletzia. And there's a lot more than just pillow basalts. There's some sandstone. There's even a little bit of limestone in there. But it was basically, the Siletzia was erupted between about 51 and 56 million years ago, and then it was added to the continent from about 51 to 49 million years ago. And then after that, you had all the younger cover sequence deposited over the top, which basically on this map are all the different colors. So if you were to take a place, say here in this light green color, and then drill a well, you would eventually you would drill through the overlying cover sequence and then into the underlying accreted terrain of Silesia. And one of the best places to see these rocks, I mean, there's a lot of great places, but really, if you just amazing scenery and everything, the Hurricane Ridge Road up in Olympic National Park is pretty awesome. You can see these huge road cuts of pillow basalts, and there's lots of places you can pull off. You can get out and you can go pet the pillows, and then you can keep driving through here. This is the road here, and it goes, the purple again, remember, is Silesia. And as you go through, then you go all the way up to the top of Hurricane Ridge, and from there you get a really fabulous view of the Olympic core, which is capped by Mount Olympus. And this whole region is called, you're in the what's called the Olympic subduction complex, or oftentimes just called the Olympic core, and that's everything inside of this horseshoe of Silesia. And so you can take a look at the rocks up there. There are some low-grade metamorphic rocks, and then you can drive down to the coast, and you can look at this, pretty much the same rocks down there, all part of the Olympic subduction complex, and you can see, amazing geomorphology down there, wonderful coastal features like the sea arch, and I just found it just an amazing area. But if you start looking closely at the rocks, you can see that in some places they consist of these debris flow deposits. This rock is a fragmented sandstone with this little chunk of limestone stuck in the middle of it. So it somehow had to get all mixed up. So you've got these submarine debris flow deposits. You can go to other beaches, and here's some really, well bedded, this is at Beach 4 along the Olympic coast, some really nicely bedded turbidites. And in fact, you can tell these things have been deformed because they're tilted, but if you've ever been there and really looked closely at the rock, you might have noticed that these rocks are overturned, because you can see there's a very sharp base here, and then it gets finer and finer grains. So these are graded beds, another sharp base, and then it gets finer and finer upwards. So these rocks are overturned. So there's, even more deformation than you might expect just from looking at them initially. But then you walk around the corner and they're just amazing. So yes, these rocks they're really variable down on the coast, and they're highly deformed. It's just what you might expect in a subduction complex. So here's a map of accreted terrains of North America. And you can see Oregon and Washington here. You can see Silesia in purple. You can see the Olympic subduction complex in yellow. And it raises the question, though, how do you know when you're on an accreted terrain? And well, for the most part, oftentimes you don't know, because most of the time you're up in the cover sequence and the accreted terrain rock is below. So it's oftentimes hard to tell, but there are some things that will clue you in as to whether or not you're on original, Paleozoic North America or not. And to give an example of that, we can just take a quick look at the Grand Canyon here. If you go to the Grand Canyon, there's the basement rock in the inner gorge, but it's overlain by this Cambrian sequence. It's very distinctive, from sandstone to shale to limestone. These rocks were all deposited during the Cambrian period when the ocean was moving up onto the continent. And we see that throughout much of North America. Yeah, I mean, we see it here in the Grand Canyon. You see it up in Utah. You see it in Montana. You see it in Colorado. I taught for a couple years at a school in Wisconsin. We saw it in Wisconsin. But you do not see it on the accreted terrains because they were all added after the Paleozoic. So if you find this sequence of rock that's Cambrian in age, you know you're not on an accreted terrain. So here in northwestern Washington, you'll notice all of Oregon, Washington are made out of, the basement is all accreted, except for the very northeastern corner of Washington state. And if you were to go up there, you can see the Paleozoic rocks that were deposited on Paleozoic North America. So here, for example, is a place called Sweet Creek Falls, which is one of my favorite places up there. And it's, well, partly because of the rocks, but also because it was usually blazing hot when I was up there, and this was such a nice, cool respite, and it was a really short walk from the parking lot. But you can see here cobbles of what's called the Addy quartzite, which was the Cambrian basal Cambrian sandstone. It's overlain then by shale and overlain by limestone. So if you were to follow this stream upstream, you could see the source of these rocks. And find them in outcrop, and there would be your Cambrian sequence. And then they're even overlain by these rocks. This is the Ordovician Leadbetter slate, and it started off as a shale, also deposited on North America. So we've got a little bit of North America in northeastern Washington. And so if you get on Washington State 20, here you can start on North America, and then you can drive westward and across the Okanagan Highlands, accreted terrains of Quinella, and then cross about a twist, you start driving up over accreted terrains of the North Cascades. Keep driving, and then you can cross over, take the ferry from Whidbey Island south to Port Townsend and get back on the Silesia. So just by following Washington State 20, you can go from North America across all the accreted terrains of Washington State. So I think that's probably, of all these roads, well, certainly one of my very favorites. Okay, so that was a little bit of the basement. And now I'd like to talk a little bit about the cover sequence. And to do that, we'll talk about the Columbia Gorge, which has Washington State 14 on the north side and Interstate 84 on the south side. In this map, you can see where the accreted terrains are exposed. Everywhere else, though, the accreted terrains are all underneath the cover and they're not exposed. So here in the Columbia Gorge, we'll be looking only at cover rocks. So here are a couple maps lifted from those roadside books. And they're just put together for the sake of the slide. The Columbia River is not this wide. This is the Columbia River here, and this is the Columbia River here. So they're just two maps put side by side. And you can see there's an awful lot of geology in the Columbia Gorge. Some of these places are highlighted here, places to see and so on. But the main rock units are here and shown in these different colors. There are these brightly colored things here and some browns are the early Cascade volcanic and sedimentary rocks. There's a whole bunch of Columbia River basalt in these brown colors. There's the Troutdale Formation, which plays an important role that I'll talk about in green. And these other boring volcanics, the Cascade Range, pretty much active basalt and andesite, or very recent basalt and andesite flows, and then of course landslides and river and flood sediments. So there's a lot there, but the main points I want to make about the gorge just is that we see in the gorge that volcanic activity dates back to the earliest Cascades. And here we basically just see that those rocks exist from Cascade volcanoes, the boring volcanics, Columbia River basalt group, and early Cascades. We see that the age of the Columbia River dates back more than 12 million years, that the bedrock structure controls the shape of the gorge, And then, of course, got to talk a little bit about the Ice Age floods, because I understand you all are Ice Age floods groupies, as I am kind of too. Actually, it was just so fun writing these books and learning more about them. So anyway, to carry on with this, we'll start driving. Oh, let me go back one slide. Oh, so as far as this little field trip goes, it really makes a great trip to like drive up 84, cross over at the Dalles, and drive down 14, or do it the other way around. They're both really different roads, but what I'll do is just kind of go from place to place to try to make it a little bit more of a coherent description. But so here are the two roads, and up above you can see I-84 in Oregon, which is a bit of a crazy highway, and Washington 14 is, by contrast, just a lovely, calming kind of drive. The road is actually very fast, but there's a lot of places to pull out and great views. I-84, though, is right at the base of the waterfalls, so they're very different. And they see some different things, so together they make for a great trip. But two things to notice here. First off, there's Mount Hood. So there's obviously the active Cascade volcanoes. But then the other thing is this mountain right here. This is Larch Mountain, which you can see from both roads. It's a large basaltic shield volcano. It's part of the so-called boring volcanics, which is a great name. They're not boring at all. They're named for the town of Boring, which is in the Portland area. Here's Portland, and here's the town of Boring. I've been to Boring, and they have a bakery. They have a sister city in Scotland. Some of you may know this, hopefully not everybody, but the sister city is the town of Dull, Scotland. Oh, good, I got a laugh. Anyway, the boring volcanics, though, are really quite fascinating. For one thing, as you can see on this map from Everts and others, they are all younger than 3 million years old. And they are all over the place in the Portland Basin. In fact, if you go to the Health Sciences University in Portland, and you can take the aerial tramway up, you get this view, and you can see all these hills around the Portland area are either cored by or consist of the boring volcanics. So they create a lot of the topography in Portland, and being so young and voluminous, they're actually considered to be a potential hazard. They've been active since 3 million years ago, and the most recently active one was Beacon Rock at 57,000 years ago. And we just don't know if, when they might erupt again. And since they're right in this big urban center, they're definitely a cause for concern. But they're also interesting because they're in such a strange place. If you look at this block diagram showing the subducting Juan de Fuca plate, and you can see where the Cascade range are. They're off the axis of the Cascades. They're much farther to the west than we might expect. And so it doesn't nicely fit in with the just plate tectonic model of the subducting plate driving, melting down deep within the overriding continental plate, because they're over a shallower part of the subducting plate. So there are various models that might explain that, but as I understand it, folks are still quite puzzled by them and still working on this. And this is Beacon Rock, which is the youngest part of the boring volcanics. It's a volcanic neck. It's I think it's either 56 or 57,000 years old. And it was greatly modified by the Ice Age floods that came down. But we'll talk about the Ice Age floods later. But you can actually hike up this thing. There's a staircase and like catwalks and stuff that go all the way up to the top. And it can give, in some places, there's some pretty nice views of the river. Oh, but behind the Beacon Rock, you can see those hills, which consist of older volcanic rock, much of which is the Columbia River basalt group. And if you go a little bit more upriver, you see a lot of the Columbia River basalt group. In fact, everything in this photograph are lava flows of the Columbia River basalt. You can trace these individual flows for miles and miles. It's quite amazing. And for those of you not familiar with the Columbia River basalt, it erupted in southeastern Washington and northeastern Oregon between about 17 and 6 million years ago, and some of these flows made it all the way to the ocean. They're also part of the whole story of the Yellowstone hotspot, so they play a really significant role in sort of western U.S. geology. But anyway, just some details about it. You can see what a big area they cover. That's more than 77,000 square miles. And the volume is more than 52,000 cubic miles. I said they erupted between about 17 and 6 million years ago, but almost all of that, 94%, was erupted by 14.5 million years ago. So 94% of 52,000 cubic miles was erupted in a period of just over 2 million years. And it's really hard to get your mind around just how much 52,000 cubic miles are. But one way to think about it is, in the Grand Canyon, the National Park Service has estimated the volume of air in between the North and the South Rim in the Grand Canyon, and it totals to about 1,000 cubic miles. And so the Columbia River basalt group was more than 50 times the volume of air in the Grand Canyon. And it followed, like I said, a lot of these followed the path all the way to the Columbia River. One of the things, there's just so much work that's been done on the Columbia River basalt, and it's got such an amazing story. But one of the things I find especially interesting is that, we've got all these amazing features in the gorge, especially those waterfalls, many of which flow over the flows of the Columbia River basalt. So here, Multnomah Falls, for example, drops some 600 feet over the Grand Ronde basalt. But the basalt itself, this is multiple flows you're looking at. And if you zoom in on the upper flow, you can see it's really kind of rubbly up here. But these are pillows within the lava flow. And so the idea here is that these flows were coming down the Columbia Valley, which were sort of an integrated system of streams and lakes. And so they would flow into the lakes and divert drainages and things like that as they made their way to the ocean. One of my favorite outcrops is here up at the Dalles, where you can see pillow basalts down here low, but it's the same flow. It's gradational up into this colonnade. And the colonnade forms on land as the flow is inflated and is basically, it's stopped moving and it's cooling down. It can form those large columnar fractures. But here underneath it flowed into a lake. So the idea is that this lava flow flowed into a lake, but kept flowing. It filled up the lake and then it flowed over the top. And then we have a subaerial flow in its latter stages. Now, another one of my favorite spots gives us some indication about the age or the antiquity of the Columbia River, which I think a lot of people can say is, well, pretty patently obvious, because the Columbia River basalts typically flowed down low areas like the Columbia River drainage. But we can see some actual direct evidence from the Columbia River at a place called Mitchell Point. And I like this sort of dumb picture because I took it out of my car window once when I was working on the roadside book. And it has the milepost right here. And you can actually go to Google Maps Street View and see the same view. And so down below is Grand Ronde basalt, which is 16 to 15.6 million years old. And up here we've got the Saddle Mountains basalt, which is, it's like 12 million years old. And so in between we've got gravels of the Columbia River. So here's a better picture of it. And here we go. And so you can see again the Grand Ronde basalt down low. And if you hike up to this area, you can see these rocks look a little different than these rocks up here. This is the lava flow, this is the gravel, and this is what it looks like. And this is an early part of the Troutdale Formation, deposited by the Columbia River. But there's even more actually, because if you zoom into the upper part there, you can see the Wanapum basalt down here, and it's in contact with these river gravels. And this is the edge of a canyon that was carved by presumably the Columbia River, in which these river gravels were deposited. And then the Saddle Mountains basalt was deposited over the top, was erupted over the top. So we've got direct evidence here of a Columbia River that is older than the Saddle Mountains, this part of the Saddle Mountains basalt. So older than 12 million years. So just to kind of summarize, at Mitchell Point, these gravels, they directly demonstrate the antiquity of the Columbia River. But also the fact that they were deposited in a canyon suggests that there was some uplift going on prior to 12 million years ago. Okay, so here's a view from Cape Horn, I think is what it's called, on Washington 14, looking up the Columbia River. And you'll notice that the shape of the gorge, it's really asymmetric. It's very steep on the Oregon side, and it's really quite gentle on the Washington side by comparison, and which really influences the shape of the influences your drive, because you're driving over much gentler terrain here. It's calmer. You're not boxed in by cliffs, and it's also a state highway as opposed to this interstate, which is right where everybody wants to go to see the waterfalls. And the reason for that is because the Washington side is prone to these huge landslides. In fact, this is the head wall right along here for what's called the Skamania landslide. And this block out in the river is part of that landslide. You can drive along Washington 14 through this landslide and go through these big road cuts, and they're road cuts into blocks, into landslide blocks. And the reason there are these big landslides on the Washington side is because the rocks are tilted gently to the south. And so as the river is cut down, that's created this sort of space where the rocks on the north side of the river can slide towards the river, and those south of the river, there's nowhere for them to go. They can't really slide anywhere down their bedding surfaces. You do get some pretty big landslides on the Oregon side, but really nothing like you get on the Washington side. So that's one of the main reasons you get the sliding, but then also the bedrock itself, it promotes the sliding, because the Columbia River basalt here in the brown is highly fractured, and so quite permeable to water soaking down through the lava flows. it gets into this Eagle Creek Formation, and it can soak through that too. It's quite permeable. And then it hits the Ohanapikosh Formation, which has an old saprolite, or basically old soil horizon at the top, which is quite impermeable. And so the water pools and it elevates the fluid pressures and buoys up the rock so it can slide more easily towards the Columbia River. So here's a view from up on Beacon Rock looking upriver. You can see this is the Eagle Creek Formation, and it's dipping gently to the south. Here's some Eagle Creek Formation. These are old lahars, about 22 million years old, I think, of early parts of the Cascade volcanoes. And they're sitting on the Ohanapikosh Formation, which is the oldest volcanic rock in the region, marking onset of the arc volcanism. I believe that some people, in fact, I think Pat Pringle was involved in this, and he's your next speaker next month, that they've discovered a few ashes and things like that that are even older than the Ohanapikosh. So it probably goes back a little farther than that. Now here's an aerial view of, you can see this big landslide. This is the Bonneville landslide. It's part of the whole Cascade landslide complex, which is just farther upstream from the Skamania landslide. You can see here the Bonneville Dam. Here's the town of, Pete's sake, I'm drawing a blank. Well, I'll think of it at the end of the talk. But here's the Bridge of the Gods, which you can walk across. It's very cool. But this landslide is about 600 years old, and you can see that it pushed the river channel to the south. Cascade Locks, that's the name of the town. And it spawned the legend of Bridge of the Gods because it dammed the river. So you could actually walk across from what is now Oregon into what's now Washington, across the landslide debris about 600 years ago. And it dammed the river, so it caused it to back up into a giant lake, which backed up all the way to the Tri-Cities area. Excuse me. But then this lake, which was impounded by the landslide, eventually broke through the landslide, and it flooded downriver, and it would have flooded Portland to a depth of about 20 feet. So really significant flood here about 600 years ago. But it was nothing compared to the Ice Age floods. Here's a view of Crown Point, and the largest Ice Age floods crested about 100 feet above Vista House. And I just like looking at this picture and imagining floodwaters 100 feet above Vista House. It's pretty inconceivable to me. And I'm sure all of you know the whole story of the Missoula spawned Ice Age floods. But just to recap, just to make sure, we've got the various lobes of the Cordilleran ice sheet have moved down into what's now the United States. And this particular lobe here, the Purcell lobe, blocked in a very similar way as that landslide blocked the Columbia. It blocked the Clark Fork, which drained all of northwestern Montana, and it backed this lake all the way up past Missoula and down the Bitterroot Valley. And to get an idea really how big this lake was, if you go to Missoula and you look up on the hillside behind the campus, University of Montana, you can see these horizontal lines, and these are strand lines from Glacial Lake Missoula. And they get to be over 1,000 feet above the valley floor. So this lake was 1,000 feet deep at the vicinity of Missoula, 100 miles away from where it was blocked by the ice dam. And you can imagine what happened when it broke through the ice dam. It coursed through, northeastern Washington, creating the channeled scablands, got into the Columbia River and flowed down the river. It backed up in a Wallula Gap here. It backed up, formed a lake all the way up to Yakima. The water made it through the gorge. At Kalama Gap here, it backed up again. It backed up all the way to Eugene, eventually made it out to the coast. And this happened 40 times, maybe there's some estimates, as I understand it, of up to close to 100 times this happened over a period of about 3,000 years. So, a flood would break, the water would break through the ice and it would flood, it would drain the lake, and then the ice would calmly advance back over the river and block it again. So on a period of every, say, 40 or 50 years, there was this gigantic flood. And of course, in the Columbia Gorge, you can see a lot of features. The scablands are amazing. I mean, there are these, you can just imagine this place with this gigantic flood tearing up all the topsoil and plucking bodies of bedrock, pieces of bedrock, and leaving behind just these remnants as scabs. The scablands are all up and down. Once you get to the Dalles, you can really see them. Of course, there's a lot of gravel deposits, which are an important economic source, but also, I mean, we see them like the aquifer, the main aquifer in Spokane is in Missoula flood gravels because it's very permeable and holds a lot of water, and so they have a really good drinking water setup, as I understand, because of this. And then there's also the erratics, which I think tell a really cool story. These things are ice rafted, so that the Lobe of the ice sheet blocked the river, but then as it broke through, you have all these gigantic blocks of ice floating down the river, carrying with them rocks as passengers. And so there's some gigantic erratics around in the Columbia Gorge and in the Willamette Valley, actually. So this is in the northern Willamette Valley, and it's located right here at the Star. Here's the Columbia River here as it makes its bend near Portland. These are the Portland Hills. This is Portland down here. And all these little dots, which you might not see very well, are locations where erratics have been found. So here, this is the Eugene area enlarged. And I just wanted to mention this kind of personal story that I have, because I had come to understand that the Missoula floods, or in general, the Ice Age floods, really, they backed up the Willamette Valley, but they really didn't quite make it all the way to Eugene. Or maybe they made it to part of Eugene, but not the very southern end of the valley. And until I went hiking around at Fern Ridge Reservoir with a friend, during the winter, the water is drawn down and it's very low, and you can walk around in the muck, which I guess he really wanted to do, and I tagged along. And so we were down in this area, and lo and behold, there's this big chunk of granite, and I found one that was even bigger, but it was kind of in the woods and not nearly as photogenic. Not that that's a pretty picture. And then here's a rock that I'm certain came from the Belt Supergroup in Montana. So there's definitely some erratics at the very southern part of the Willamette Valley. So these floodwaters, they backed all the way down to the edge of the very southern part of the Willamette Valley. Okay, so there's a lot in the Columbia Gorge. It's all cover sequence, but you can take all these different rocks and you construct a pretty simple cross-section doing this. where starting with the early Cascades volcanic and sedimentary rocks in blue, and you've got the Columbia River basalt group in brown, the boring volcanics here, the more recent Cascades volcanoes. Here's a little bit of Troutdale Formation and landslides and so on. And you walk through that history and you can basically see that, yes, there's all these different things in the Columbia Gorge, that the volcanic activity goes way back to early Cascades. The age of the Columbia River, based on the Troutdale Formation and the location of the Columbia River basalt, dates back more than 12 million years. And we see that the bedrock structure controls the shape of the gorge. And of course, there's a lot of Ice Age floods evidence in the gorge as well. But if you take this cross-section and just compare it to the more regional one, you can gain a little more perspective on it. I mean, for one thing, you can see, the Columbia Gorge area is just in this vicinity. So we're not even touching the basement rock. But you can also see that the cover sequence is really much even more variable than what we see in the gorge, and it goes on and on and on. And that on and on and onness, if you will, I think that's what I love so much about geology, is that the story really never stops. The more you learn about it, the richer the story becomes, and then you create more questions, and then that starts filling in more details, and then even more questions. It just goes on. And just to kind of to drive this point home, here's Mount Rainier, which is this incredible dormant, but basically recently active and will erupt again in the future, almost for certain, Cascade volcano. It's got the most topographic relief of anywhere in the United States. It's covered in ice. And it has an amazing history. If you were to wander around on Mount Rainier and get to know its rocks, you would see that it's got all these lava flows, andesitic lava flows that certainly makes it contrast markedly with, say, Mount St. Helens to the south. But these lava flows have their own story, where a lot of them occupy ridge tops. And the story now is that these lava flows they basically flowed right down the ridge tops because there were glaciers on either side of them, confining them to the ridge tops. And you would see that it's got its own basement, the Tatoosh Pluton, which has its own history that goes over a period of about 10 million years of various intrusions. And then there's bedrock all around it that shows volcanic history that's even older. And so Mount Rainier, though, is just one volcano in this whole range of Cascade volcanoes. And that whole range of Cascade volcanoes is just represented by this little triangle up here on the cross section. And so there's just so much, and wherever you go, you find something new, and the story just gets richer and richer. So thank you all for letting me go on and on about the geology that we all know and love in the Pacific Northwest, and I'll be delighted to take any questions you might have.